can you just little bit help that what is the post of business means? What people do in business development assistance?
We'll discuss about one to one. Okay, guys. So before starting for today, any questions from the last session?
Chandra, hi, Prerna this side. I have a question, Chandra.
Prerna, 1 second. Yes, Prerna. Yeah.
So, Chandra, can you please explain homoscedasticity once? I mean, I think that's missed or I did not get it.
Sure, sure. Okay. Any other questions?
And even, I mean, we did not touch upon the gradient descent thing, the cost function.
That we will discuss. Don't worry about that.
Okay. Thank you.
Yeah.
After creating the dummy, we're using the get dummies, and if we do the D-type profile, it is coming U int 8. Do we have to convert that into int 64 while appending it to the main data frame?
Not necessarily.
We can use that.
Not a problem. Okay. The homoscedasticity is very simple, guys. So this explain about the relationship between your x and y. Suppose this is x and this is your y, and if the relationship is something like this. So basically what I'm saying is in the, if suppose x is increasing, your variance of the data is increasing y. Suppose here you have very less variance, but whereas if you look at this one, the variance is very high. So that means that the variance is not constant over the time. So not time, I mean to say over the x. So this is what we call it as a homoscedasticity, sorry, heteroscedasticity. If the data is following homoscedasticity, I mean so that I'm expecting that the constant and the variance is constant. So suppose something like this, if you see here, what is that? It is just variance is almost constant everywhere. So this is what we call as a homoscedasticity, and this is what we call it as a heteroscedasticity. So ideally, we need to have homoscedastic data. So suppose if this kind of a data you have it, most of the times the log of x or log of y can, applying the transformation like log can help you to reduce the variance, so that nothing but your, your data will be more or less constant variance over the x. Is it clear, Prerna?
Yes, Chandra. I mean, whenever, just another request. So whenever you're sharing the code, can you also include the script to check this? I mean, in the results.
The results, the script is, obviously the script is something what you can think about is, just look at the scatter plot between your y and each x, that's all.
Okay. And should I be doing this before the building the model?
See, generally, that is we already almost taking care when we have the data of, following a normality. Some extent you are taking care of this aspect also. Because what happened when you are converting into normality, you are removing the skewed part. The removing the skewness, it's all automatically you are removing some kind of variance in the data. So
Correct.
some extent you are taking care of your outliers and the normality and all of these things if you are doing, and the linearity relationship between your x and y. These three some extent take care of your heteroscedasticity issue. So that's the reason generally we don't really give a lot of importance to this one, because this is anyway these three things automatically taking care.
Okay.
Okay. But yes, generally if you want to strictly follow the assumptions, of course this thing you need to look at. But generally what we say is when I'm taking care of the remaining three, this automatically problem get automatically resolved.
Chandra. Thank you so much.
Okay. Any other questions? Okay. So guys, there is two concepts I need to talk about. One is the gradient descent algorithm, and there is another one which I need to talk about, MLE. So these two things I will talk about probably when I'm introducing machine learning part, because at this point of time explaining this one will not that much make sense. So we will discuss about the gradient descent algorithm and the maximum likelihood estimation. Both the things I will talk about probably once you get comfortable with some level of understanding on the terminology. Is it clear? So especially I will introduce, when I'm going to introduce this machine learning concepts, there I will talk about these two things. And of course, there is one more concept like stochastic gradient descent. So this is also, I will talk about these two things as part of the machine learning concepts. Okay. So today, my objective of session is, so yesterday we have done a regression problem using OLS regression, right? So the next type of problem is, a classification problem. Right? So the classification problem, is something which we want to solve. So now tell me, what is a classification problem? As I said that this is one of the common problems which we see in day-to-day work. So I think, as I said, that 60 to 70% of your problems related to classification. But fortunately, whatever you are done with the regression problem and whatever you are going to do with the classification problem, the process will be similar. So that means that the 70% of learning related to classification problem, you already done it in a regression problem itself, right? The 70% of learning related to solving classification problem done in the regression problem itself. Does that make sense what I'm saying? What I'm saying is, whatever the approach which we followed for regression problem, whatever the approach which we are going to follow for classification problem, the concepts remain same. So only thing is the technique, the application, the interpretation, the metrics, these are the 4 areas which you will see there is a difference. Okay. So now tell me, what is a classification problem? If y is categorical variable, then we can say it's a classification problem. So divide the data into email spam. So email detection, type of mail. Okay. Churn versus not churn. Customer is fraud or not. Okay. What else? Any other examples which you want to tell? Customer buy versus not buy. Fraud versus not fraud, churn versus not churn, and by what you can say, whether customer is going to claim insurance amount or not, claim not claim, renew or not renew. That's also some extent fraud only, right? Okay, so renewal or not renewal. Okay, we will win the bid or not. Okay, so like this, a typical data, suppose a customer is leaving or not leaving, what you will have is, okay, customer ID and your X1, X2 and X2, x3, x4, and suppose like this, you have xn and you have y. For example, customer, you have the data like this. And you will have a customer is good or bad, a churn or not churn, risk or not risk. Like for example, 1 or a 0. So what does this mean? A 1 means good customer, a 0 means bad customer, or vice versa, whatever it is, or churn, not churn. So basically, what I'm saying is you will have the data of existing data. This is my existing data, right? What you want to predict? So you will have your customer ID and your X1, X2, and so on, XN. And your Y, you need to predict. You need to predict. So this is what exactly we are looking for, the existing data. So this is the place we will try to establish a mathematical relationship between your X1, X2, and so on, Xn. You will predict Y is 1 or 0. Right? So are you able to follow me? Any questions on this? So I think this is very clear, right? A simple example is banking. It's a very common problem which we see is in the NPS. What is NPS? Non-performing assets. What do you mean non-performing assets? So the customer is not paying back whatever the loan he took, right? So this is a very common problem for banks in nowadays, right? So I think they are making a lot of losses, or they're doing a lot of charge-offs, because of this. So to control those losses, what will you do? So there are two types of control you can do. One is for the new customers. When we are giving the loan, we will be a little bit stringent. Stringent means for everyone we will not issue the loan. What we'll do, we will identify which customers will pay, which customers won't pay, and that is the place which customers are good, which customers are bad, and accordingly we will give them a loan. That is one kind of a caution we can take. The other caution is, okay, when customer is not paying, so immediately we need to take some action, like before they are become charge-offs, we will try to collect their money using different strategies. Correct? Or in next 3 months a customer is not going to pay. Before that itself, we will take some kind of a precautions so that you will get your money. Right? So this is what a typical kind of a process which we call as, that's what we call as a credit risk management. Right? Mitigating the risk, or mitigating the losses, or reducing the losses, optimizing your collection process. So these are the typical examples which we can talk about. So in this case, there are a couple of things which you need to understand. The variable what you have is not in a continuous in nature. Correct? So this is not a typical regression problem. This is a classification problem. Now my question is, if I have y variable like this, can we apply linear regression on this? Okay, if we apply, why not? You can apply. If you don't apply, why can't we apply? What is the reason for that? So indirectly what I'm saying is, to solve classification problem, why can't we apply linear regression? Indirectly, if I apply linear regression on this data, what is the problem? What is the problem, guys?
I think we can actually use, because the target has only two things, yes or no. If there are more values in the categorical variable to predict, then we can. Okay,
even I'm talking about 2 variables, I'm talking about 3 variables also. Sorry, 3 categories also.
So Chandra, in linear regression problem, we are looking at a linear continuous relationship. Here the relationship is not, It's either 1 or 0, right? It's not continuous.
See, that is our intuition. What I'm saying is, I'm asking that if I apply, what is the problem? So you are saying that you will get the output as a continuous result. So that means if you are getting the output as a continuous result, I can take some cutoff and say that, okay, greater than 0, I will call it as a 1, less than 0, I will call it as a 0 or something like that.
In category, we are predicting taking probability, and if you are applying the regression, so the probability can go below the 0. Negative.
What is the probability here? What is the relation with the probability?
Probability of whether we are getting the 1 or 0.
No, here I don't know. I want to get my 1 or 0 because that is my objective, right? Because I'm not asking the likelihood of a customer is going to pay or not. I'm asking that, it's anyway the variable is there. If I apply on this data on a linear regression, if I apply it, what is my consequences? What is the problems? If I don't, why can't we apply? That's what I'm saying that. So the main problem, I think someone, Santosh mentioned that, if you look at, if I want to apply a linear regression, first of all, what I should have it should follow my assumptions. What are my assumptions? Y should follow normal distribution, or Y and X should have a linear relationship. Correct? So in this case, what I was referring is, what I'm referring is, if I want to apply linear regression, what I need to do? I need to convert my Y into some variable such that Y, the new variable should follow normal distribution. So that is the first thing I need to target to look at. Is it correct or not? So this is what exactly you need to think about. So in this case, first, since my Y is not following normality, I cannot, this is one of the assumption. And the second one is, if you look at my Y and X, this is my Y and this is my X. So if I look at the Y and X, what is your Y and X relationship? So Y is always 0, 1, right? So assuming that this is a 1 and this is 0, so this is 1. So that means that for every value of my X, either you will have 1 or you will have a 0, right? Assuming that, these two values you have it, either you will have 1 or you will have a 0. So for every value of X. Now, if I have this data, can you say that, is there any linear relationship between these two? Is there any linear relationship? No, right? If you look at this one, if I look at this kind of relationship, obviously this is not a best fit relationship, given that the data is maximum error. Correct or not? So the Y is not following normality, and the data is not, Y and X won't have a linearity relationship. Am I correct or not? So that means if these two fails, what can you do? Obviously, you can't really use the linear regression. Okay, are you clear now? So I think even yesterday I was referring something concept called generalized linear models. What do you mean that? Yes, your Y is converted into some apply. So that means that Y transformed into Z such that Z equal to a function of Y. Okay, then if Z is follows normal, then I can apply linear regression concept on this. Correct or not? So this is what exactly we are going to do here. Okay, so now the question is, what is my right transformation? For example, if I have the data y equal to 100 kind of a thing, what is the right transformation I should choose? Because that is what we are not sure, right? Because yesterday, you remember, if the data is following exponential distribution, what did we do? We applied log transformation. But if the data is following a binomial distribution, what transformation I should apply? That is something which you need to figure it out. Okay, so that means that what is the best transformation or a link function for converting y into z such that z follows normality or linear regression. Is it correct or not? Yes or no? Okay. So this is the one concept which we need to identify. That is nothing but what is the link function I need to identify. Okay. So now coming to the other point. Suppose you have a y variable and you have some x variable, like for example, x variable is z. So x variable is age. X variable is age. So that means that x is age and y is, for example, churn. Okay. What I exploratory analysis perspective, I'm saying that the age and the churn has some relationship. Age and churn has some relationship. So when can we say that? When can we say that age and churn has relationship? So I mean to say that age is a continuous variable, churn is categorical variable. Now when can we say that these two variables are related?
By performing an F test.
Sorry? Okay,
By
F
performing
test. Okay, if you perform F test, what is the F test output?
It will give me a F statistics and a p-value, and
Okay,
I can.
what is the F statistics means? I mean, what is that tells me interpretation perspective?
That if I mean their relationship is significant or not.
No, that is I understand, but I'm saying that what is that F test is doing there?
It's that's what I understand, that it will compare a relationship between the two and will tell me
No,
that if
you are perfectly correct. I mean, you understand, I mean, whatever you mentioned, it's correct. I'm saying that F test will help you to identify the relationship between categorical and numerical. But I'm
Yes.
saying that what is that relationship means, you know? So I think if you guys remember or not, so the F test or a T test will help me to compare means of multiple samples. Correct? So what do you mean multiple samples? I mean to say that, for example, if I take churners and non-churners, these are two samples I can think about. For a churners, I have 50 customers. A non-churners, I have 150 customers. You know, the age of these 50 customers and the age of this 150 customers I can calculate. So the age of 50 customers I got as a 55, and the age of this one is 28 or maybe a 30. So what does that tells me? That in the lower age group are non-churners, higher age group are churners. Can I say that? Or vice versa, maybe, you know, this group may be having a 55 age, this group is having a 30 age. So what does that mean? What does that mean? The young customers are more churners, and old customers are non-churners. Can I say that? So this is what exactly, if I want to say some relationship exists, I need to identify some relationship, right? The age and the, the churn. Then only I can say that there is a relationship exists. Suppose both the groups are having a similar age, what does that mean? Can you say that age is influencing your churn or not, or any way kind of relationship exists or not? Can you say that? I can't say that, right? Do you agree with me or not? So this is what exactly I'm saying, that whenever the F test is telling me, F test tells me that, okay, you have 2 samples or 3 samples or 4 samples, and it will compare the means of that numerical variable. Suppose in this case age. Suppose if I want to see the segment and income is having any relationship, how can we say that? Okay, S1, S2, S3. There are 3 segments, assuming that, and the average income is, for example, here also it's 3 lakhs. Here is 3.05 lakhs. Here is 2.99 lakhs. So do you say that is there any relationship between your income and segment? I don't think so, because all of them are having a similar kind of income. If they have a different incomes, then I can say that there is a relationship. Because some segment have a higher income, some segment have a lower income, then I can say that, okay, the segment also has a relationship with your income, because different segments have a different incomes. Correct or not? So this is what I'm saying, that the relationship between 2 numerical variables. Oh, sorry, 1 categorical and 1 numerical. So now if I consider this concept, let's assuming that I have the age and the churn variable. So the age is your X variable and your Y is churn, assuming that there is a relationship. Assuming that there is a relationship. The relationship is, for example, the churners are more if the age is high. The churners are more, the age is high. Maybe some age some customers with low age also, some of the people got churned, but the majority of customers who are having a high age, they churn. That means the old customers are more churners, and some age customers also stayed back, but majority of your customers are churners if the age is high. So can I say that there is a relationship exists in this case? Now in this kind of scenario, linear line cannot be a best fit line, because that is not going to give you a best relationship. So this kind of situation, what is the best fit line I can think? The best fit line I can think is whichever line can pass through maximum number of points. In this case, if you look at some kind of a S curve, if you think some kind of a curve like a S curve, the S curve can be a best fit line or not? Yes or no? So that is what, the best fit line. If you want to achieve this as a something, then I need to perform some kind of activity around it. So indirectly what I'm saying is, if your Y and X has a relationship, a best fit line for this relationship can be the sigmoid curve. This is nothing but the S curve. The S curve is nothing but what? The sigmoid curve. Yes or no?
Chandra, could you please repeat that once again? The last.
So, what I was referring is, if the data, there is a relationship between your Y and X. So what does that mean? So in our case, age and churn. So the relationship is something like this: a higher age, high number of churners. So that means that the age is increasing, the churn percentage is increasing. Suppose this is the relationship you have it. So that means that what? Anyway, your Y and X have 1, 0. So Y is always having 1, 0. That means that high age, you can see maximum churners. This is a 1. This is a 0. So lower age, you will not have so many churners. There, most of them are zeros. And higher age, most of them are 1s. right? So that means that some low edge also you will have, some high edge also you will have, zeros. Some low edge also you will have churners, but majority of churners are what? High edge, you have a high number of churners, and low edge you will not be any churners. So suppose if I want to come up with a relationship like this is the place. What is the best relationship I can think about it? What is the relationship I can think about it? So in this case, the relationship can be, if a line with some kind of a sigmoid curve is my best fit line, instead of taking a linear line. So the linear line cannot be a best fit line in this case. The best fit line, is S curve. S curve, or we also call it as a sigmoid curve. Do you agree with me or not? Yes or no? Are you able to follow me, guys? Any questions? I think this is very clear, right? So now what I'm saying is my output should be S curve if I want to establish a relationship. Okay, if I want to get output as S curve, what is the general form of S curve? Suppose a linear line is what? Y equal to mx plus c. But for a S curve, what is the general form? So this is what I was trying to explain now. So the general form of S curve. Okay, so general form of linear line, linear equation is what? Y equal to beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus and so on beta n xn plus constant. And the general form of S curve is basically what? Exponential of beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus and so on beta n xn plus constant by 1 plus exponential of beta 1 x1 plus beta 2 x2 plus and so on beta n xn plus constant. So basically this is, I'm saying that it is a e power, suppose the linear line by 1 plus e power linear line. So this is the the general form of sigmoid curve. Suppose if you look at the sigmoid curve is always the values gives between 0 and 1, because it's always between 0 and 1, right? Because denominator is 1, so denominator is higher value and numerator value is low. So obviously this will always give you between 0 and 1. So that's the reason if you look at my output of my line equation, so this always will be between 0 and 1, correct? So that means that if I come up with this line, okay, suppose if I'm calling this line is P, so what is my P value will be? P equal to, so assuming that my linear equation is this one, and what is your P value? The P value is what? E power exponential of L by 1 plus exponential of L. Is this clear? Okay, this is my target, guys. So that means that if I want to get the output, I am looking for output something like this. If I get this output, I am able to achieve my best fit line, which can give me the a good accuracy, which will pass through the maximum number of data points.
Chandra, can you please repeat this formula? What is P? What is P?
I'm saying that this is the general form of general form of sigmoid curve.
Correct.
That is, I'm calling as a P. Okay, so for the timing, I don't know about the P for the timing. Okay, just I'm giving the output of this one, I'm calling as a P. But only thing I know is the P is always between 0 and 1, correct? This is the only thing I know because based on the formula. Okay, so this is the one concept you should keep it. So there are three concepts I discussed now. One is a GLM concept. One is sigmoid curve concept. Okay, so if a numerical, a categorical variable and a continuous variable, if there is a relationship, how can we establish the relationship? With the help of sigmoid curve, because that can be a best fit line instead of a linear line. Correct? Okay, cool. So now,
the value of P between 0 and 1, or it should be either 0 or either 1?
No, between 0 and 1, because that is the value you will get it, right? You take any x1, x2, x3, x4, xn, you take any values, the L is, some value you will get it. The exponential of L is always a positive value.
Yes,
By positive value by 1 plus positive value, this always give a between 0 and 1.
Okay, fine.
And another thing, Chandra, so in the GLM concept, you are saying that for linear regression, y is continuous, and we perform any transformation on that and make it either 0 and 1 with a link function, right? So then we can apply a GLM concept on it. This is what you're saying.
I think you understand reverse manner. So I'm saying that since my y is 0 or 1, I can't apply the linear regression. So for that, what I need to do, I need to apply some kind of a transformation on y such that the new transformed variable is continuous form, so that I can apply the linear regression.
Okay, thank you.
Okay, so now let's understand this concept. Okay, so now you know the GLM, now you know the sigmoid curve concept. Now, how to marry these two things? Okay, so this is the marrying part. You will I mean, by marrying these two concepts, you will achieve the link function. You will achieve the link function. So how will you achieve? That's what let's understand. So now what you know, P equal to e power L by, exponential of L by 1 plus exponential of L. So this is what you know. Suppose, of course, L is nothing but, I told you, it's a beta 1 x1 plus beta 2 x2 and so on, beta n xn plus constant. Okay. Now what I'm saying is, if I take this one, can I say that L equal to, or P by 1 minus P equal to L, sorry, exponential of L. So just I'm applying some kind of a mathematical thing. So P equal to e power L by 1 plus e power L. That is same as a, suppose if you, cross multiply and then you can get the, finally you will get, if I want to calculate the exponential of L, then you can get this value in the left side. Of course, if you do little bit maths. Okay. Now, what I'm saying is, if this is the case, what I need to do, log of P by 1 minus P is L. So that means that what is my L in this case? Correct? Yes or no? So that means that if I look at my linear regression, what is my linear regression in, what is your right side? My right side is linear equation, right? That is nothing but beta 1 x1 plus beta 2 x2 plus etc. What is my left side? left side is your y. That is there, your linear regression, your left side is dependent variable, right side is linear equation. Correct or not? So my right side part is same as exactly linear regression part. Now, what is my left side? If I'm able to convert my y into log of p by 1 minus p, then of course this is, if I'm converting to this one, can I apply this as a linear regression? Am I correct or not? So this is what exactly I'm trying to do. So that means that by assuming a general form of sigmoid curve is this one, and this is the kind of relationship I can establish. If I want to consider this is my hypothetical relationship, what I need to do? I need to achieve my y need to be transformed into log of p by 1 minus p. Correct? So if I want to achieve log of p by 1 minus p, so of course there is a a proof or theorem is created. What is this mean is, if I'm able to achieve log of p by 1 minus p, this is same as a probability of y equal to 1 by 1 minus probability of y equal to 1. Okay, so that means that, okay, this transformation, okay, so your y converted into log of p by 1 minus p, this is what we call it as a logit transformation. So this is logit transformation is log of p by 1 minus p. So that means your y converted into log of probability of y equal to 1 by log of probability of y equal to 1 by 1 minus probability of y equal to 1. This is same as a log of probability of y equal to 1 by probability of y equal to 0. Correct. Because from my general form of sigmoid curve, this is the kind of relationship I'm able to establish. But if I want to apply linear regression, my y need to be transformed into in this manner, then only I can apply linear regression concept. So that means that how can I convert this one into this one? This is the logit transformation which I'm saying that this is a theoretically proved. Correct. So indirectly what I'm saying is, if your generalized linear models will help you to convert your y into logit of y. The concept of why we are taking logit? The logit is the transformation which will help me to convert your y into logit of y, and the logit of y is your left side of a hypothetical relationship of the sigmoid curve you want to achieve. Right? If this is the line, then only I can achieve my p-value like this, right? Correct or not? So this is what exactly you need to understand. If you understand this concept, I think the rest of the concepts like applying linear regression concepts only.
Chandra, can you please repeat that statement? Right, written against line number 56. P by 1 minus p.
So what I'm saying is, the p equal to e power l by.
So over here, p mean to say a probability.
So that time I don't know. Now I'm saying that theoretically we proved that the p is same as a probability of y equal to 1. Okay, so this is nothing but the p into 1 plus e power l equal to e power l, right?
Correct.
So now, e power l, you can go to the right side. That is nothing but p equal to, 1 minus p into e power l. Yes or no?
Yes, Chandra.
So then that is nothing but e power l equal to p by 1 minus p.
Okay, yeah.
This is what I was saying, that is the simple maths you need to look at.
Fine. Okay. And from there, the next step would be we are taking the log, right? converting that into.
Yes, exponential, you can, if it comes to the left side, then it will be a log, because
Correct.
log and exponential are opposite functions.
Okay, fine. Okay.
Chandra, line number 59. So I get it that log of p by 1 minus p is nothing but the linear equation. But then what did you do next? Y is equals to 1. I mean, how is this coming?
So I'm saying that if I want, because end of the day, I need to marry these two concepts. What are the concepts to need to marry? I need to achieve this relationship. If I want to achieve the relationship, I need to convert your y into log of p by 1 minus p. So what is that log of p by 1 minus p in terms of, the conversion perspective? The p is nothing but the probability of y equal to 1.
Okay, p is the probability of y equals to 1. Okay.
Correct. So indirectly what I'm saying, let me explain this one. So suppose your customer ID is there and your x1, x2 and x3 and x4 and your y is there. Suppose in this case, 1, 2, 3, 4, 5, 6, 7, etc. and 1000. And now assuming that my x1 is a location and your this one is sure. So location Bangalore, Gurgaon, Chennai, Delhi, maybe Vizag, Delhi, Chennai, etc. So assuming that, I have location and of course, in this case, you have 0, 1s, etc. 0, 0, 0, 0, 1, 1, 1, 1, 0, something like that. So location and that's nothing but number of ones and number of zeros. Correct? So that means that okay, location is Bangalore and Chennai and Gurgaon and Delhi or Vizag. Suppose these are the different locations you have it. Out of 10,000 customers, okay, there are 3,000 customers that belongs to this one, 2,000 customers that belongs to this, 1,000 customers belongs to this one, and 1,500 customers that belongs to this one, and 2,500 customers that belongs to this one. In this, my number of bad customers, that means number of churn customers is 2,000, right? So and this means that 8,000 customers are here. So out of this, if you look at Bangalore, the Bangalore I have is almost 800 customers that belongs to Bangalore, and there are 200 customers that belongs to this one. There are not 200, maybe 50 customers that belongs to this one, and there are 500 customers that belongs to this one, and there are 300 customers that belongs to this one. So that means total how much? 350 customers that belongs to this one. And that's nothing but 2200 and 1950 and 500 and 1200 and how much it is? 2150. Correct? So this is basically what? Total customers. And now probability of y equal to 1 for this one how much? And probability of y equal to 0 how much? Probability of y equal to 1, 800 by 300, 3000. Correct or not? And this is nothing but 2200 by 3000. So this is my probability for 1 and 0. Now a log of probability 1 by 1 minus probability of this one. This is same as basically what? Log of this divided by this. Correct or not? Right? So indirectly I'm saying that if I have only one x1 variable, my my y is transformed into what? Log of probability of 1 by 1 minus probability 1 minus probability of y equal to 1. Correct? So that means that suppose if I don't have any variables, assuming that these are the only one variable I have it. Now how my value, wherever Bangalore is there, I will replace that this value with the minus 0.43933. And wherever Gurgaon is there, what is the value of log odds? 0.5, right? Correct or not? And the Bangalore, of course, minus 0.49, so 43933. Oh, sorry, it's 0. So wherever Chennai is there, minus 1.59 something. Like this, I can replace this value. Suppose if I have two combinations, one is location and one is age, then for those two combinations, what is the log odds? So that is your dependent variable will be calculated behind the scenes. Of course, you don't need to do all of these calculations, but I'm saying that how you are relating the concepts. Are you able to follow me now? So that is how you converting y into log of probability of y equal to 1 by probability of y equal to 0. So now instead of taking this variable, I'm going to take this variable, which is nothing but continuous variable. You will get it.
One quick clarification, Chandra. So the link function here is the logit function, is it?
Correct.
Okay, thanks.
So, so Chandra, in line number 61, I mean, we have this logit transformation, and then you're just saying that this is probability of y is equals to log of probability of y is equals to 1 divided by probability of y is equals to 0, right? And this is what is called as log odds ratio.
Correct.
And this is what the transformed y is using the logit transformation as a link function.
Correct.
Okay.
So indirectly I'm saying that y is transformed into log of probability of y equal to 1 by probability of y equal to 0. And sometimes people also call it as a log odds ratio. This is odds ratio. Okay. Now I think if you understand this concept, once I know this one, what is the next thing I need to do? Just apply the linear regression concept and get my betas and get my equation, and once I get this relationship, then my output will be P, right? This is not my ultimate goal. My ultimate goal is P. So to estimate my betas, I'm using this relationship because I know linear regression concept. Correct or not? Once I get this equation, what I will do that I will convert into P. So that is what my output. So indirectly what I'm saying is, if I get a linear regression, sorry, if I solve the classification problem with this technique, what is your output? The output will be P, because that is your best fit line, not the linear equation, right? My output is my sigmoid cost. That is my best fit line. So this is what you will going to get it as part of output phase. And since we are applying this transformation called log odds, this is what we call it as a logit transformation. And the logit transformation, since we are using, we call it as a logistic regression. Or sometimes people also call it as a logit regression. Right? So what does that mean? Y transformed into logit of y, that is same as a log of P by 1 minus P. Then you will apply your linear regression concept to estimate your betas. So once you are trying to solve this one, what are the things? Again, it converts into optimization problem, and you will solve the optimization problem with the help of gradient descent or maybe maximum likelihood estimation. Some methodology we use it, and we will try to achieve the betas. And once we get the betas, and we will use this relationship to come up with my p-value.
So Chandra, what would be the cost function in this algorithm then?
So the cost function is end of the day when we are doing the optimization problem. So end of the day, of course, if I use a methodology called MLE, the cost function will be, the likelihood function. We'll discuss about that later point of time.
Okay, I mean there will be a cost function, and will
for every problem, whenever we are estimating betas, I mean any kind of a parameters, all the problems will solve with the help of optimization. When you are solving optimization, you will have cost function, because without cost function or without objective function, you cannot solve an optimization problem. So to solve optimization problem, you should have a cost function. How will you get the cost function? What is the algorithm you use? For example, in the linear regression, what is the algorithm we used?
OLS.
Minimizing sum of squares of error. So there your cost function is SSE, sum of squares error. Here, generally we use the cost function is MLE. Cost function is, basically I will tell you, it's an MLE, which is nothing but maximum likelihood estimation. It's a, MLE is the method we use, maximizing likelihood estimation. What is the for cost function is log likelihood ratio. Okay, so this is for logistic regression.
So
Not
will
only
we-
logistic regression, any kind of generalized linear models, we use this one. This is what we call as MLE, right? So linear regression also what we solve. My cost function is basically what? Sum of squares of error, right? So, and of course, even linear regression is a special case of generalized linear models also. How? So for example, your y is following something and you have a link function, and for example, suppose y is following a what distribution? Suppose y is following a normal distribution. What is your link function? Identity function, because there is no change, right? Because we want to get identity function. And if it is a log normal distribution, then we will use exponential. And if I use exponential distribution, you will use log as a link function to transform the data. So that means then it will become normal, and it will be normal, it will become normal. And if the data is following a binomial, then logit function is something so that the after the function, which is nothing but the function of y. Correct? So that means that even if the data is following a normal distribution, still I can apply identity function and it will convert into generalized linear models. So for a generalized linear models, the cost function is MLE. That is nothing but log likelihood ratio. Okay, we'll discuss about what is log likelihood ratio at a little later point of time. At this point of time, you may not able to digest that concept. We'll discuss about little later point of time. But at this point of time, what you need to do is you are converting into optimization problem, and you are solving the optimization problem with the help of gradient descent. But how to convert into optimization problem? Only thing you need to know is cost function. Once you know the cost function, it's just a matter of solving the cost function. That is what we are trying to call as a solving optimization problem. Does this make sense? Any questions online, guys? Okay, so I think what my the discussion till now, what I'm doing is, okay, for example, if my data I have it x1, x2, x3 and x4, after performing all the optimization and solving the optimization, you will get your output is P. Correct? Because that is my best fit line which I'm going to achieve. Okay, now assuming that okay, for example, 9, I have 10 customers, assuming that, and you have 1, 0, 0, 1, 1, 0, 0, 1, 1, for example, like this you have it. So now what you will get the output, which is nothing but P is nothing but what? Probability of y equal to 1. So probably you may get 0.7 here, 0.3 here, 0.2 here, 0.4 here, 0.55 here, 0.6 here, Okay, so something like this, you got the p-value. Okay, one important thing is when you're getting the output of p, what you are trying to get it is the sum of y will be same as the sum of the probability. So this is the one constraint when it's solving the logistic regression optimization problem. Okay, the sum of p is same as a sum of y. Okay, so this is the output you will get it, guys, after doing the model building. Yes or no? So once you get the model, so once you get the output, now what is my next question? Of course, once you build the model, this is what you got the output. Of course, end of the day, once you build the model, you will get the p equal to exponential of beta 1 x1 plus beta 2 x2 plus and so on, and beta n xn plus constant, and by 1 plus exponential of beta 1 x1 plus beta 2 x2 plus and so on, beta n xn plus constant. So what is known things in this? Sorry. 1 second, guys, 1 second. Knowns are what? x1, x2, x3 and so on, xn, and of course, in this case you also know about your y. Correct. What is unknowns? Betas, right? Beta 1, beta 2 and so on, beta n and constant. So you will solve that problem. You will solve the relationship log of logit of y is equal to beta 1 x1 plus beta 2 x2 and so on, beta n xn plus constant, right? So that means that you will, after solving this equation, what will you achieve? After solving this equation, you will get the values of beta 1, beta 2 and so on, beta n and constant. So that means that I will have this relationship. So once I know the relationship, I will get my value is this one. Correct? Okay, this is my output of my model, guys. My output of model is this one, the p equal to. Using that, I can calculate my probability of y equal to 1 for my training data as well as testing data, whatever it is. Yes, someone having any question?
Yeah, Chandra, one question I would like.
Your voice is coming very low. Who is speaking?
Yeah, I'm Santosh. Am I audible?
No, not really. I think your mic or something, probably you need to check it. Okay, guys, any other questions you have? I mean, till now you're clear now? Okay, now suppose this is my output. How can we ensure that your model is good or not? So if you remember, in linear regression, once you get the predicted value, how did you ensure that your model is good or not? One is by looking at the sum of squares of errors, that is, R square. How did we calculate the R square? You remember? That is SSC by SSD, that concept we used it. So by using that, I can achieve my R square or RMSE or MAP to tell that how good is your model. But in this case, how will you compare that? Because one is in categorical, one is in probability. You cannot use, the subtraction and you can look at the, 1 or 0, right? It should be in the same scale. Of course, in this kind of scenario, you cannot use the same methodology what we followed. Correct? So now, in this case, what are the different metrics we have which can help us how good is your model? This is a place, there are two types of outputs you will have it. One is based on the output as a probability. Okay. So once you have this output, generally this is not my final output, right? This is not my final output. What is my final output should be 1 or 0. Because end of the day, I need to predict 1 or 0, not the, what is the probability of a customer is become bad or become churn, right? So of course, this is also you can use as a business perspective, but I'm saying that what is my ultimate goal is, this one. So this is the place generally what we do is we take some kind of a cutoff. Okay, assuming that my cutoff is 0.5. Then what is my values of this one? Okay, this is 1, this is 0, this is 0, and this is 0, this is 1, this is 1, and this is 0, this is 1, this is 0, this is 1, correct? Of course, now important thing is how to decide the cutoff, that we will talk about little later. But at this time, think about if this is the cutoff you use and you got this output, and based on that I can identify which customers are correctly predicted as a 1, which customers are wrongly predicted. Suppose this customer you are predicting as wrong, right? And this customer you are predicting as wrong, and this customer you are predicting as wrong, and this customer also predicting as wrong, correct or not? So these are my misclassification done. So that means that what you can say there is based on output as categorical variable after choosing a right cutoff. Does that make sense? So if this is my output, what is my accuracy matrix? And if this is the output, what is my accuracy matrix? Right? So these are the two aspects which we need to understand. Suppose if this is the thing, what is my accuracy matrix? This is what I'm trying to explain that. Okay, let's talk about this first and then we'll come back to the probability part. So if this is the case, your actual values are what? And your predicted. Your predicted is 0, 1 and your actual is 0, 1. And so total in this case, how many customers are there? 10. Out of that actual ones, 5, zeros 5. And the predicted also 5 zeros, 5 ones. Maybe you can see that. How many ones are there? 1, 2, 3, 4, sorry, 4. 4 ones and 6 zeros, right? This is what you print. Where 5? Oh, sorry, 5, correct. Sorry. Whatever it is. So now how many zeros, actual zeros you predicted as zeros? Okay, this one, and this one. These three are predicted as zeros correctly. Okay, and how many ones you predicted as ones? 3. That means that 2 zeros predicted as a ones and 2 ones predicted as zeros. Correct? Because if you look at this one, and this one predicted as 0, and this one predicted as 0, and similarly this 0 predicted as 1, this 0 predicted as 1. Correct? So this is what we got it. Now in terms of the accuracy, how can we say that? So how many zeros correctly classified? How many ones correctly classified? How many zeros correctly classified as zeros? How many ones correctly classified as 1? So that means that this one and this one is correctly classified. So that means what is my accuracy? 6 out of 10. Am I correct or not? So this is a one simple metric you can think about. Are you able to follow me? And this metric, we call it as a misclassification. This matrix, this comparison, whatever we are doing. So if you think about this one, the actual total 10 customers we have. Out of that, 5 of them are 0, 5 of them are 1s. And the predicted 10 you have, out of that 5 of them you predicted zeros, 5 of them predicted as a 1s. But the accuracy is how much? 60%. Okay, now let's understand one more thing. So this is, suppose the table you got it something like this. Okay, you predicted 7 of them zeros, 3 of them this one, and that means that this is 0. That means that he predicted 5 here and he predicted 2 here. Okay, assuming that this is the table you got it after some cutoff. Now in this case, what is your accuracy? Accuracy is 5 plus 3 by okay. And suppose sometimes you want to identify accuracy for ones. How many ones correctly classified as ones? So this is what we call it as a this is what we call it as a sensitivity. Sensitivity is nothing but, okay, out of total 5 ones, how many ones you correctly classified? 3 by 5. And the specificity is opposite. Opposite means what? How many zeros correctly classified as zeros? In this case, how much? 5 by 5. 100%. Correct or not? Okay. And this is what exactly we call it as. And this is also, we call it as a okay, so the in terms of the terminology, we call it as this is a positives. Okay, so let me explain this one. So in terms of the terminology, sometimes people use this terminology. Okay, this is we call it as a negatives, and this is what we call it as a positives, and this is negatives, this is a positives. Okay, if I say that positives correctly classified as positives, this is what we call as a true positives. Negatives correctly classified as a negatives, this is what I call true negatives. And negatives you classified as a positive, this is what we call as a false positives. And positives you classified as a negatives, this is a false negatives. Right? So if you think about this one, my accuracy is nothing but what? Tn plus Tp by total. Correct? And sensitivity is Tp by Tn plus Tp plus Fn, because the sum of these two is 5, right?
Chandra, why Fn? I mean false negative.
That means that this is a true positives by 5. That is your sensitivity, right? That means
So,
5. How did you get it? The sum of these two.
Okay, so sensitivity is correct classification of ones, of
Correct.
actual ones.
Correct.
So true positive by false negative. Okay.
Yes. Specificity is true negatives by true negatives plus false positives, because that is the sum is 5. So this is we call it as a TPR, guys. This is a true positive rate, and the specificity is the true negative rate. Okay, and 1 minus specificity. What does this means? 1 minus specificity is nothing but 1 minus of Tn by Tn plus Fp. So this is same as a Fp by Tn plus Fp. Correct or not? Because at the end of the day, you are subtracting this one. So this is same as a this one, and this is what we call as FPR, false positive rate. Okay. Now let's understand. If my model is good, your accuracy also should be high, and your sensitivity also should be high, and your specificity also should be high. So this one is high and this one is high. correct? And of course the accuracy is also automatically high. But some scenario, if this one is high and if this one is low, still accuracy can be high, because here it's as equal proportions. But sometimes, you know, you have, you know, suppose 7,000 customers belongs to positives and only 2,000, 3,000 belongs to negatives, then positive negative rate can different from accuracies. But end of the day, what I'm saying is you should have less proportions over here. In the other than diagonals, the false positive and false negative should be low. That is same as the true positives and true negatives should be high. Is that correct? So that is what exactly we need to look at. Okay. Yeah, sorry.
Sensitivity should be high.
Sensitivity should be high and specificity also should be high. Our sensitivity should be high. Our FPR, that is nothing but 1 minus specificity, should be low. Correct? Okay. Now what I'm saying is, if this is the table, if this is the cutoff and this is the table, I got it right. If my cutoff got changed, what is my, suppose if I take 0.4 as a cutoff. Okay, P is greater than 0.4 is cutoff. So then my value will be 1. Of course, 0 here, 0 here, 1 here, 1 here, 1 here, 0 here, 1 here, 1 here, 1 here. Whatever it is, it doesn't matter. So end of the day, what I'm saying is, I will get a different table over here. If I get a different table, my sensitivity will be different, my specificity also different. So that means that for a different cutoffs, of P, you will get different values of sensitivity and specificity. You will get different values of sensitivity and the specificity. So that means that, okay, my cutoff is 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, and so on, like this, 0.99 or 9, whatever it is. So I can get a different cutoffs, and I will also get the accuracy. I will also get the sensitivity and specificity, and of course 1 minus specificity. Okay, suppose I got the accuracies here 55%, and here 70%, here 69%, here 72%, something like this you can happen. And similarly here 60%, here 40%, here 39%, here 82%, something like that you got it. Then I can get that like this, I can get the table for cutoffs and sensitivity and specificity and accuracy metrics. Yes or no? And if I take this one, so I can decide the cutoff by using this table. How to decide cutoff? Whichever cutoff gives me high accuracy. So I can use any of this methodology to choose the best cutoff. Whichever cutoff gives me high accuracy, or whichever cutoffs gives me high sensitivity, or whichever cutoffs gives me high specificity. So these are the typical approaches we do, but generally what we do is whichever cutoff gives me high sensitivity plus specificity, the total, because at the end of the day I should have a high sensitivity and high specificity. The summation is whichever gives the high sensitivity plus specificity, and that can be the one of the best cutoff to choose. Or you can also look at the accuracy. Okay, so this is the methodology we will use to choose the best cutoff. No, so I mean to say that that is the table, you will get it for a different cutoffs. Of course, end of the day, if you get this table and you can choose what is my best cutoff. Yes, you will choose from this only. 0 to 1 in between any value. I don't know which value. Maybe you can take 0. First you will start with 0, 0.01, 0.02, 0.03. Then 100 cutoffs you will get it out of that which table, whichever cutoffs gives you a best, that will be chosen. Right. So it's conceptually this is the one. Of course, in Python it's just a matter of 2 lines of code or 3 lines of code. It's nothing matter. So don't worry about that. So the implementation perspective is much easier, but I'm saying that the conceptually you need to understand what it means. Okay. Now, if I take this sensitivity and if I take this 1 minus specificity, if I draw a line or draw a graph, so the graph is something like this. What is the graph? What I'm saying is this is my x-axis is 1 minus specificity. Okay, and this is a sensitivity. Okay, if I draw a line for a different cutoffs, and my line will be something like this. Okay, so what is this line? This is what we call as a ROC curve. The ROC curve is nothing but what? The ROC curve is a graph between a 1 minus specificity and sensitivity. So ideally your model is nothing but what? You should have a low 1 minus specificity and high sensitivity. So if a model I'm getting, that model gives me low 1 minus specificity and high sensitivity, that is my best thing. Suppose this is my model 1, I got it. And another model I got it is something that how if you do that, I'm getting like this. So what does that mean? So this is my M2. So assuming that, which model is best? M2. Why? Because for a lower value of your 1 minus specificity, you are getting the high sensitivity. So that means that my M2 is better than M1. Do you agree with me or not? So that means that, can I say that the area under the curve for M1, the area under the curve for M1 is lower than the area under the curve for M2? Do you agree with me? So that means that this is one metric I can also calculate. So what is the calculation I can do is, I can calculate AUC is nothing but area under the ROC curve. If area under the curve is high, AUC is high, can I say that my model is good? Yes, this is the another metric which we call it as the area under the curve. Right? So any questions on this? Okay. So there are
Chandra?
one second. There are 2 set of metrics I was talking about. If I know my ultimate output is a categorical output, I know that all these metrics. What are the metrics? Accuracy, sensitivity, specificity, and all of these things. And if my area under the curve, only if I know the probability, based on the probability, I can calculate my ROC curve. How? By getting this kind of a table for different cutoffs. You have accuracy, we have a sensitivity, we have specificity, and I can calculate sensitivity and 1 minus specificity. I can draw a line and I can calculate the AUC. So if my AUC is high, my model is good. Or if my accuracy is high, my model is good. My sensitivity is high, my model is good. So you can choose all these metrics to think about it. So in this case, what I'm saying is, if I think about based on the probability, one of the metric we calculate is AUC. And in this case, what is the metrics? Accuracy, sensitivity, and specificity. And there is one more thing I need to talk about. Of course, I will discuss about that. There is a precision and a recall and a F1 score. So these are some more metrics. Based on that, we will discuss about that. And AUC, and of course, there are a few more metrics like a concordance and discordance and SOMAS-D, or that's also called as Gini, and gamma. These are all our different metrics based on the probability we'll calculate and based on the categorical as a output, and this is my matrix. Correct. Once you decide the cutoff, once you get the cutoff, and I can get these metrics, right? But to achieve the cutoff, what I need to do? Calculate for different cutoffs, sensitivity and specificity, etc., and identify a best value of cutoff, which gives me high sum of sensitivity plus specificity, or maybe high accuracy. One of the methodology you can choose. Once you get the cutoff, these are the metrics. But before getting the cutoff also, I can tell that whether my model is good or not by looking at the AUC. Because for the AUC, you don't need any cutoff, right? Because if I know the probability for different cutoffs, I will get the sensitivity and specificity, and based on that, I can calculate the ROC curve, and by using that, I can calculate my AUC. Yes, guys. Any questions now?
So, Chandra, in the ROC curve, we are plotting against false positive rate and 1 minus specificity and sensitivity. What is the reason for that?
The reason for that is I want to see that, of course, ROC curve can help me in two ways. One is identify the best cutoff, and the second thing is whether my model is good or not. So the reason I'm saying that, ideally my model is good. When can you say that my model is good? With a low 1 minus specificity and high sensitivity.
Okay, that means low false positive rate and high true negative rate.
Yes. How good is your model? By looking at that only I can say that. Of course, by using these tables also I can say that, but the same thing in a visual manner, nothing else. So whatever you are getting over here, it is exactly the same thing I'm talking about. Sorry, for different cutoffs. I think we discussed about for different cutoffs in a tabular manner. I'm showing that the same thing I'm showing in a visual form.
Okay. Okay.
Is this clear? Yeah. Any other questions?
Is 1 minus specificity equal to sensitivity?
1 minus specificity is equivalent to FPR, right? That is what we are discussing here. So true positive rate is sensitivity, and specificity is true negative rate, and false positive rate is 1 minus specificity. Okay, cool. Okay, there is one more interesting concept. Okay, if I know these two things, because at the time of model building, I don't know about the cutoff. At the time of model building, only I know that, okay, this is my Y value, these are my predicted values. Because based on my betas, I can calculate my P value. So at the time of model building, I know that only P as an output. So in this case, I told you one of the metric is AUC. What are the other metrics? So let's understand this concept. Okay, assuming that this is the data I have it. So if my model is good, if my y equal to 1, my probability of y equal to 1 should be high. For ones, you should have a higher probability. For zeros, you should have a lower probability, because since we are predicting the probability of y equal to 1. If that is not happen, what does that mean? The model is not good. Because you are predicting is wrong, right? Because that's what you are saying that. So if my model is good, my probability of y equal to 1 should be high for ones. Probability of y equal to 0, y equal to 1 should be low for zeros. So because end of the day, probability of y equal to 1, and that is same as a 1 minus of, probability of y equal to 0, that is same as a 1 minus of probability of y equal to 1. That means that it will be 0.3, it will be 0.6, etc. Since we are predicting probability of y equal to 1, so you should have higher probability for 1 and lower probability for 0. You are agree with me or not? If you are agree with that, so now can I compare these two? Of course. Do we have higher probability for 1 and compare it to zeros? So that is what I'm going to do the comparison. Okay, which of the customers are ones and which of the customers are zeros? Customer 1 is 1, customer 4 is 1, customer 5 is 1, and customer 8 is 1, and 9 is 1, right? And what about zeros? 2, 3, 6, 7, and 10. And what are the probabilities for 1.3 and 0.55 and 0.4? Oh, sorry, I think I got confused with this. Okay, sorry. So it's a 0.7 and 0.45 and 0.6, 0.55, 0.45, right? These are my ones. And what about this one? 0.4, 0.3, 0.7, 0.3, 0.55, right? Okay, now ideally if my model is good, I should have a higher probability for ones and a lower probability for zeros. So is this, suppose if I'm taking this one, if I'm comparing with customer 1 with other customers in terms of the probability. Okay, if I compare 1 and 2 customers, is that correctly, you are having a high value for 1 and low value for 0? So that means that, can I say that this is satisfied the criteria? And what about this? This is also satisfied, right? But here, which one is high, you don't know. It's a ties, because this is also 0.7, this is also 0.7. So the ties, probably I cannot really comment on anything around that. Yes or no? And again, these two are lower than 0.7. And what about this guys? 0.45 is higher than this one and this one, but this one, is it higher? No, right? It's a reverse happened. It's a, zeros have higher probability, ones have a lower probability. And what about this? Correct. And what about this? It's exactly similar to this one, and of course this one. And what about this one? And of course, in this case, first 4 are same, and one tie, right? And what about this one? It's exactly the same as this one, right? So that means that if I compare, how many comparisons you are doing? So total comparisons, total pairs. So 5 ones and 5 zeros, 25 comparisons you are doing. Out of that, how many pairs are having the criteria satisfied? So if criteria satisfied, this is what, yellow and red. These are the things. So these pairs, a pair is satisfied the criteria we call it as a concordant pairs. Concordant pairs. And these we call it as a discordant pairs. And these we call it as a ties. Out of total pairs, how many pairs are with the concordant pairs? So 5, 10, 15, 17 total.